Now that I've defined the unit step function and the window function in my last video, let's look at taking the transform of these. So I want to take the transform of the step function u of t minus a. This means the integral from 0 to infinity of e to the minus st u of t minus a dt. Well, that would be the integral from 0 to a of e to the minus st times 0 plus the integral from a to infinity of e to the minus st times 1. This whole thing goes to 0, and this is minus 1 over s e to the minus st between a and infinity. So that'll be the limit as n goes to infinity of minus 1 over s e to the minus sn minus negative 1 over s e to the minus as. As n goes to infinity, this term here is going to go to 0. So the actual transform, e to the minus as over s. The next one I want to do is the transform of the window function a to b. Well, this will be the integral from 0 to infinity of e to the minus st times, and I'm going to go ahead and define this window function, times pi of a comma b dt. This will be defined from 0 to a. I would have the integral of e to the minus st times 0. From a to b, I have e to the minus st times 1. And from b to infinity, I have e to the minus st times 0. So my first and third terms are just going to go to 0. The integral of this middle one is minus 1 over s e to the minus st between a and b. This then gives me minus 1 over s e to the minus bs minus negative 1 over s e to the minus as. So I'm going to rewrite this as e to the minus as minus e to the minus bs over s. So this would be the transform of the window function. Now that we have the transforms of the window function and the step function, what I really want to be looking at is the transform of f of t minus a ut minus a. So I have shifted my step function as well as shifted my function. This is going to be the same as e to the minus as times the transform of the original f of t. In addition, if I try to take the transform of a function that's not shifted, just f of t times ut minus a, so only my step function is translated over, this will be e to the minus as times the transform of f t plus a. So I'll have to translate it over by a in the opposite direction. So let's look at some examples of this. Here I have the transform of t minus 2 squared ut minus 2. In this case, they both have the t minus 2. So this is going to be e to the minus as, so minus 2s, times the transform of f of t. So instead of t minus 2, I'm going to change this to just a t and have t squared. That would then be e to the minus 2s, and the transform of t squared, according to my table, is 2 over s cubed. So my actual transform, 2 e to the minus 2s over s cubed. This time I want the transform of t squared u to the t minus 2, and this time I only have a t minus 2 here. So the rule says it's e to the minus 2s times the transform of, and then I'm going to do t plus a. So I'm going to shift this. Instead of t, I'm going to write t plus 2 squared. In order to take that Laplace transform, I'm going to go ahead and multiply this out and get t squared plus 4t plus 4. So I would have e to the minus 2s times. The transform of t squared is 2 over s cubed. The transform of t is 1 over s squared. In this case, it will be 4 over s squared. And the transform of 4 is 4 over s. So here I have the transform of t squared u t minus 2. This time I have cosine t times u t minus pi. I only have the t minus pi, the shift in the u function. That tells me this is going to be e to the minus pi s times the transform of cosine of t plus pi. And so this would be e to the minus pi s. And cosine of t plus pi is the same thing as negative cosine t. So we would have negative e to the minus pi s times the transform of cosine, which is s over s squared plus b squared. And in this case, b is 1. So here I have my transform. This time I want the transform of cosine t minus pi u t minus pi, and I have the t minus pi in both of these. So that tells me I'm going to have e to the minus pi s times the transform of just cosine t. So this will be e to the minus pi s times s over s squared plus 1.